Identification. So identification is a fundamental concept in statistical inference, and it's a concept that we should think about prior to and actually separately from estimation. For causal inference, achieving identification is a necessary condition. It's something that we must do in order to have a causal interpretation of the data. And in principle, it's very simple. Identification simply concerns whether it's logically possible to uniquely determine the value of model parameters given sufficient observed data. So we can think about that in terms of an infinite number of observations. So we have a formal definition here. A parameter theta for a family of distributions, fx, x depending on theta, is said to be identified if distinct values of theta correspond to distinct PDFs or PMFs, distinct distributions. That is, if we have a value theta prime that's not equal to theta, then the density parameterized by theta is not the same function as x as that parameterized by theta prime. So, two different structures we have here of theta lead to two different unique solutions. If that's the case, then we say that the family of distributions is identifiable. We're able to identify it. If it wasn't the case, if this property did not hold, if these two densities here could not be distinguished, if we could not distinguish one parametric form from another, then the two structures of the model are said to be observationally equivalent. We can't tell one apart from the other. Now, the existence of multiple observationally equivalent structures implies that a model is not identified, because if observations from both distributions look the same, then we cannot know whether the true value of the parameter is theta or theta prime. And that precludes a causal interpretation of a model, because there's more than one structure that will generate the observed data. And in general, we can't have a causal interpretation, or certainly that idea that we can have two different interpretations of the same model is inconsistent with the statistical notion of causality. So we saw that in the examples we just looked at of confounding. In those cases, there was more than one explanation for the association between y and d, and that means that those models were not identified. So to make this more concrete, let's now illustrate the concept of identification in the linear model setting, y equals x beta plus var epsilon, for both unconfounded and confounded structures. And as I said previously, we're going to use the linear model for analytical derivation, but this intuition or identification generalizes regardless of the parametric form of the model. So let's look first at how the linear model is identified when things are unconfounded. So from the definition we've just given of identification, we can state that the linear model is identified when this property here holds. So x beta equals x beta prime, if and only if beta and beta prime are the same. So all that's saying is we can't have multiple versions of beta that give us the same fitted value. Now there are two conditions that are required for identification. First of all is the population orthogonality condition, as it's called. This is simply Gauss-Markov condition 3, which states that there is no correlation, no covariance between the covariates and the error term. And the second condition is expected full rank. This just means that the matrix is non-singular, and that allows it to be inverted. We talked about that in a previous lecture. So the important one really is this one here, Gauss-Markov condition 3, which has actually been really important. We don't talk quite as much about it, but it's key in this lecture. Now, to see how these two conditions identify beta, we're going to pre-multiply the linear model up here by the transpose of x, and we're going to take expectations, and we're going to use the population orthogonality condition to say that the expectation of xt x transpose error term is equal to 0. Multiply this through, we get x transpose y, x transpose x beta plus x transpose a. We take expectations, we do a bit of matrix algebra, we rearrange, and this gives us this expression here. And what that shows is, that as long as this condition here holds, which managed to get rid of the error term that we don't observe up here, then as long as we've got data in x and y, sufficient data, then we can always calculate a unique value of beta, because it can be written in terms of population moments in observable variables. So under the unconfounded conditions, the linear model is identified. Now we're going to look at what happens when things are confounding. As we said, confounding arises when we've got a misspecified model that excludes some important influence that's embedded in the DGP. And in the linear model, excluded effects arise from missing covariates, simultaneity, and so on. In the linear model, those missing effects end up in the error term, and the error term therefore becomes a composite of both random and systematic or deterministic components of the model. And as long as that systematic component of the error is correlated with the covariates, then the Gauss-Markov condition 3 is no longer going to hold. So we violate the population orthogonality condition that we used here to achieve identification. Just doing some simple matrix algebra, what you're going to see is that this leads, our expression for beta is now this expression here. Importantly, this term here doesn't disappear because it doesn't equal 0. We can't assume that because x is not independent of the error term. And therefore, this is no longer identified model because we don't observe the error term. And therefore, we cannot find a unique solution here. The solution that we achieve is going to depend on the error term and the assumptions that we make about the correlation between the error and x. But this model is not identified. No matter how much observed data we have, we can't evaluate a unique solution because it involves the unobservable E. Now the identification problem resurfaces at the estimation stage. Applying least squares to the model under confounding, we get this expression here. As we know that from lecture 5. And that expectation there, so the expected value of beta is equal to the true value plus this term here. But that term here can't be factorized into an expectation based on x and an expectation based on var epsilon, because the two are not independent, and therefore we cannot factorize the expectations as we know. So the OLS estimated is biased. It equals the true value of the parameter plus this biased term here. It's also inconsistent because for exactly the same reason in the probability limit, as we take the probability limit of these terms, we cannot assume that this expression here will tend to 0 because x is not independent of v. So in other words, we apply a large law of large number here, and we cannot use this condition here, which we'd use if things were unconfounded, because Gauss-Markov 3 would be satisfied, but it's not, so we can't. So this term, the bias term, does not disappear. So in the presence of confounding, the linear model is not identified because the expressions we end up with involve the unobservable error var epsilon. Different versions of var epsilon with different correlations with x will use different solutions for beta. So we have observational equivalence, we don't have a unique solution. And a full derivation of the above result in the context of confounding for omitted variables is given in the proof slides. And if you want to compare that with the unconfounded case, go back to lecture slide 5 and look at slides 28 to 29. I mean, you can go through this really in your own time, so it's very simple, but all we're saying is, suppose this is our true model. The true model is y equals x beta plus w gamma plus an error term. These are confounding omitted variables, variables that we don't observe that we're going to put into the model. The true model satisfies Gauss-Markov condition 3, but we don't observe w, so instead we focus on this model here, where the error term u equals w gamma plus var epsilon. So we just subsume those confounding covariates into the error term. And that means that Gauss-Markov condition 3 fails because there's correlation between x and w's ended up in U. So as we just said, that means our assumed model is not identified because we can write it in this form here, and it can't provide a unique solution in the unobservables Y. But turning to estimation, this is the least square solution we get. If we expand Y, we can write that expectation in this form here. And this term here will disappear because the expectation of xte is equal to 0. So this will disappear, but this will not disappear. That's a non-zero confounding bias, which doesn't go away. So the incorrect emission of confounders W from the assumed model produces a biased estimator, in the sense that the expected value of our estimator is not equal to the true value of the parameter. And that's the case because this holds according to the true data generating process. And it's also inconsistent because, for exactly the same reason, this expression here will not converge to 0. Thus, confounding bias and inconsistency are going to result as long as there is an association between emitted variables and the covariates. That's the definition of confounders. They are correlated with the covariates and they're correlated with the response, and the emitted variables should appear in the model. So as long as there's confounding, we're going to have a problem. So if a model is not identified, then we cannot find a unique solution for parameters based on observational data. And failure of identification can lead to bias and inconsistency in estimation and invalidation of inferential statistics. So to keep things really simple, just to demonstrate what the bias looks like, we're going to look at bias and inconsistency from a very simple confounding situation. So suppose the true model is y equals beta naught plus beta 1 times the treatment plus beta 2 times x and an error term. If we omit x from the regression and x is genuinely a confounder in the sense that it's not only relevant for y but it's also correlated with d, then beta 1 is going to capture a double effect. It captures the direct effect of d and a proxy effect that mimics the effect of x on y. It's very easy to show that under confounding, the estimate beta 1 will be biased and inconsistent by the amount given here. So the expected value of beta 1 will equal the true value of beta 1 plus beta 2 times covariance of d and x over the variance of d. So see how it's incorporating this confounding? That's what's ending up as confounding bias. And this gives us an actual analytical expression for the theoretical bias that we would get by excluding x from this model. So the important principle here is to achieve identification, we do not have to represent the entire DGP in our model, just enough of it to eliminate confounding bias. That's the guiding principle that underpins causal inference. We've talked about the problems, we've talked about non-identification and confounding, and we're now going to look at how causal inference can be used to solve those problems.